Hello everyone. Today we are going to study large language models. These are the powerful AI systems behind tools like ChatGPT that have captured the world's attention. Let us understand what they are and how they actually work. Large language models are sophisticated next word predictors. Imagine a magic machine that, when given any piece of text, figures out what word should come next to continue the sentence. This seems to be a simple function, but it is a fundamental building block of all LLM models. When you interact with the chatbot, the model takes all the previous messages in your conversation, including your latest input, and treats it as a one long string of text. Then it predicts the next best word for the AI's reply. It adds that word and then predicts the next word based on the new longer string, and so on. This iterative prediction continues until a complete and sensible response is generated. This is exactly how chatbots and large language models work. They predict one word after another based on what is already written or said. It is important to understand that LLM don't just pick one word for any given input. The model assigns a mathematical probability to every single word it knows, indicating how likely each word is to come next. So if the text is "the dog barked at," the words like cat or mailman would have high probabilities, while the words like mountain would have very low probability. Instead of always picking the same word, these models decide which words are most likely, making replies that sound natural and interesting, even giving different answers to the same question sometimes. To ensure the output is not repetitive or bland, LLM often introduce a degree of randomness. Instead of always picking the most probable word, they can sometimes pick a slightly less probable one. This makes the conversation feel more natural, more human-like. This randomness is typically controlled by a parameter called temperature. A higher temperature leads to more creative and diverse responses, while a lower temperature makes the output more predictable and focused. How do these models become so good at predicting? They learn from vast library of text data. This includes almost everything publicly available on the internet: books, articles, websites, conversations, code, and more. The scale is difficult to comprehend. For example, the training data for a model like GPT-3 would take a human reading 24 by 7 over 2600 years to process entirely. This massive exposure to language is key to their understanding. The intelligence and behavior of a LLM are encoded in billions of adjustable numerical values called parameters or weights. Think of these as tiny internal knobs that determine how the model processes information and makes its predictions. The largest LLM today can have hundreds of billions of these parameters. It is this immense number of adjustable parts that allows them to capture the incredible complexity of human language. As the model trains, it tunes the parameters. These decide how the model predicts the next word. At the beginning, the parameters are totally random, so whatever it predicts is just nonsense. Then the training starts, the model is shown huge amount of text. For every line it tries to guess the next word, that guess is checked against the real word. If it is wrong, the mistake is used to make tiny adjustments in those billions of parameters. This process is called backpropagation. The same cycle is repeated trillions of times. Slowly, the model becomes sharper and better at predicting the next word. Large language models have hundreds of billions of these parameter dials. In the start, they make random guesses, but with training, they keep learning and finally start giving smart and meaningful predictions. While the process looks straightforward, the computational scale is truly staggering. Adjusting billions of parameters trillions of times requires immense computing power. Training the largest LLM involves millions of GPU hours, consuming vast amount of electricity and requiring highly specialized hardware. This underlines the incredible engineering and resources invested in building these advanced AI systems. Training these models is a massive job, so big it would take a single person more than 100 million years to do it by hand. The initial training makes an LLM excellent at predicting the next word in any given sequence. However, the goal for a chatbot like ChatGPT is not just to predict the next word, but to be a helpful, harmless, and honest assistant. These two objectives are not automatically aligned by the core next word prediction task alone. This is a crucial second stage of training, reinforcement learning with human feedback. In this phase, human evaluators interact with the model, asking questions and rating its responses based on the criteria like helpfulness, accuracy, and safety. This human feedback is then used to further fine tune the model's parameters, teaching it to generate responses that are aligned with human preferences and avoid unhelpful or harmful outputs. It is a powerful way to guide the model's behavior towards desired outcomes. The speed and scale of LLM training and operation would not be possible without specialized hardware, graphic processing units, or GPUs. Unlike traditional CPUs, GPUs are designed to perform many calculations in parallel, making them perfectly suitable for the massive concurrent data processing required by these models. The big change came in 2017 when Google's researchers introduced the transformer model. Earlier models used to read text step by step, one word at a time, but transformers can look at the whole sentence together in parallel. They also use something called attention to understand the correct meaning of each word in context. This change made language models much faster, smarter, and more powerful. Since computers work with numbers, not words, the first step is to convert text into numerical format. Each word is transformed into a long list of continuous numerical values, often called vector or embedding. Crucial words that are semantically similar, like king and queen, will have numerical representations that are close to each other in abstract mathematical space. The true genius of transformer lies in its attention mechanism. This allows the numerical representations of each word talk to other words in the input sentence. This interaction refines each word's meaning based on its surrounding context. For example, the word bank takes on a different meaning in river bank compared to money bank. Attention helps the model check this and build a much richer understanding of the entire sentence, even across long distances within the text. Beyond attention, transformer models also contain feed-forward networks. These layers provide additional computational capacity, allowing the model to store and recognize even more complex language patterns, grammatical structures, and semantic relationships. They act like highly specialized memory banks for linguistic rules, and they are constantly refining the model's ability to generate appropriate text related to the context. Most fascinating aspect of LLM is their emergent behavior. While researchers design the architecture and the training process, the model often develop capabilities like common sense reasoning or problem solving that were not explicitly programmed. The specific why behind a model's every prediction often remains a complex puzzle, even for its creators. This black box concept, where intelligence seems to emerge from a scale, is one of the most active and exciting area of AI research today. The fundamental mechanism behind every LLM is sophisticated next word prediction, the transformer architecture, and refined by human feedback. LLMs are rapidly transforming how we interact with each other, marking a new era in artificial intelligence. The journey of language AI is still just beginning. So when you use a chatbot, it's always using its training and making word predictions that are good and human-like, even though we don't always know exactly how it decides.